All right, so now that we've talked about a little bit about EDS in general, and that was in the context of wavelengths, or sorry, X-rays being the incident beam, we're going to talk about EDS that is in an SEM, or a scanning electron microscope. So with the scanning electron microscope, the beam for imaging is electrons. And so this uses electrons for EDS instead of X-rays that we talked about with XRF. So that's the only difference. So this diagram in your book shows the geometric arrangement of EDS in an SEM. So this has become pretty commonplace for modern SEMs to have EDS because it gives elemental analysis. And so this is kind of a typical arrangement. So the pole piece, which is part of the imaging arrangement in SEM, so part of basically the lenses and so forth. The electrons are beamed at the sample, which is down here on top of the stage, and the detector for EDS is over here on the side. And again, it has a collimator, which makes everything parallel and so forth. But it's off to the angle over here with respect to the specimen. So it's somewhere over the angle. So this angle between the specimen surface and the detector, so basically this angle here, this is known as the takeoff angle. And so we can actually change that angle in the machine if we have, and all machines will have the ability for the specimen to actually rotate. So we can actually rotate this from side to side and change that takeoff angle. And so the reason I brought this up is because our next question in the quiz is going to be about this takeoff angle. So we've talked some about EDS and just the general arrangement here. So can you envision any problems that will occur if this takeoff angle is really small? So you could think about the detector being even lower to exaggerate a low takeoff angle. So what problems maybe can you think of that would happen if we have really low takeoff angles? So see if you can brainstorm some ideas and write them down in the quiz, and then come back and we'll talk about a couple here. Okay, so you paused it, you come back. So now let's talk about the result this low takeoff angle can occur. And so this next figure in the book kind of illustrates what can happen. So let's take a much finer look at a sample surface. So a sample surface may be rough like this, like you see. And if the electron beam is coming down perpendicular to the sample surface, and the detector is over here at this sort of low takeoff angle that you see, then the topography and the microstructure that happens could actually sort of cause some of these X-rays that are emitted from this region here to be absorbed or deflected or redirected by this feature, this sort of hill feature over here. So if we're in this valley feature, then the features over here could actually obscure the X-rays from going to the detector at these very low takeoff angles. So rough surfaces definitely interfere with the collection of X-rays. And so one issue here, or one way to solve this would obviously be to get a flatter surface. So that's one way that you can do it. The other way is you can, again, rotate the sample surface. So if you rotate it such that this angle is higher, then more of those X-rays are going to tend to get to the detector. And so we can either make the sample smoother. If that's not an option, we can try higher takeoff angles by rotating the sample. So this is one of the reasons, this is just one of the effects of this sort of geometry that we have. All right, so one of the reasons why we choose to do EDS inside of an SEM and not just on a standalone instrument is because when we couple these two instruments together, it allows the potential to analyze a very small area of the sample. So instead of looking at the whole sample, we can now just analyze a small portion. And so this is sometimes referred to as micro-analysis, when we're just looking at a very small spot size instead of the whole bulk material. And so that's the important feature of putting an EDS inside of an SEM. The SEM allows us to image very small places, and the EDS allows us to analyze very small places. And so that, but both of the minimum areas that you can identify are going to be governed by the electron beam. So we have to have a very small electron beam to be able to do that. So let's look at that portion. So let's look at this electron beam. So the electron, and let me go back to the slides here. So the electron beam comes in, and the first instinct would be that, and so this is just showing within the material. So this is within the material. So if you just kind of focus on this portion now. So this is the electron beam converging onto the surface of the sample. And so your first instinct might be to say that the electron beam diameter at the surface dictates the area within the material. And that's not necessarily the case, because what we see is that electrons, these are at high energies. So for example, 20 keV, these electrons can penetrate deep down into the sample by this value R. And so they actually interact with a very large area. And we actually call this the interaction volume. Since this is a 2D representation, it's actually a volume. So we call this the interaction volume. So this is the area in which these electrons can interact with the material. And they're also have to do with the X-rays as well. So once X-rays are produced, how far can they escape? So that's the other portion that we have here. And so let me switch back to the slides, and I'll show you the relationship between this interaction volume and the beam voltage that we have. All right, so this is the drawing you saw before. So this is again, the sample surface here, and then the electron beam, and then the interaction volume that we saw, which sort of has a teardrop shape. And so this interaction volume that we see is not constant. It varies depending on the beam voltage. So the electron, so I'm abbreviating electron as this, beam voltage is what we call E naught. So that's the beam voltage. And so the radius here, or sorry, the size of it, which we call R here, so basically the depth of this teardrop is related to this value. So essentially we can relate this R term as 0.064 times the product of E naught to the 1.7 power minus EX to the 1.7, and then that's all over this density term. So just to kind of rehash this, R is the emission depth. So we're saying that this is roughly equivalent to the emission width. And then EX that we saw on the bottom there, or sorry, on the top, is the energy to excite a given characteristic X-ray. And then rho is the mass density. So what we see is that if we want to decrease this emission volume to have the smallest possible volume to interact, so basically we have microanalysis, so we're trying to get as small area as possible, then we want to typically decrease this. And one way we do that is by decreasing the beam voltage in this case, right? From this equation, we can decrease the beam voltage here, all else being the same. However, typically we want to, we also have to consider some other factors. We have to consider this energy of the characteristic X-ray. So to optimize resolution, you can see we want to choose a beam voltage just slightly above the energy of the characteristic X-ray. So there's issues between the interaction volume and also the energy of the characteristic X-ray. So the other factor that goes in here is that you get a smaller interaction volume, R, with increasing density. So if we're comparing different materials, more dense material compared to less dense, then we get a smaller interaction volume. So that's another issue. So the resolution of SEM, which we'll talk about in the next section on SEM, is going to be tied to the microanalysis that we can do, how small we can make this. So we still need to kind of talk about the resolution. So I'm not going to get carried away with it here. But one of the things that we often see is that the resolution is much better in TEM because we have really thin samples. And so we're basically just dealing with a very thin slice of this. And so we don't have to deal with the kind of the broader part of the teardrop down here. So TEM has much better spatial resolution because of these thin samples and because we don't have this large part of the interaction volume. And so we can get much better, much narrower bits. So doing SEM and TEM is even better if we're trying to get as small of a option as possible. So that's also, again, with TEM, we also have a much higher energy, and that can also cause the size of this to go down as well. The higher energy we have, the probe current, so this diameter that we have, tends to go down as well. But again, we'll talk more about this when we get to SEM and TEM. For now, you don't have to worry about that quite as much. Just the main idea here is that if we're trying to look at microanalysis, the beam itself and the interaction volume will be two things that we have to consider, and we'll go in more detail when we hit SEM and when we talk about TEM.